All right, let's talk about the method of joints. So the method of joints is how we actually analyze trusses. And what we're doing, remember, the first thing we do is we take the truss and we separate it from the rest of the world and we find out the reaction forces, right? Maybe we're given P, we're given some lengths and angles, and then we calculate these reaction forces, RA and RB. And then, yeah, so that's that one. And then we do look at the members of the truss. So let's walk through this. We break this down into two force members. So for example, this member AC has got two forces acting on it, right? All these members have forces acting on them. And then we look at, okay, what are the forces acting on the pins at each location? Now, if you know a reaction force, so for example, over here, you know this reaction force, right? The first thing you can do is you can come over here and you can figure out, all right, I know this force. I can write a geometric relationship between these two forces. I can do some of the forces in X and Y and figure out these forces, right? And depending on the direction of these forces at B, that's going to indicate which direction they are acting on the member, right? So for example, if something is pulling at B, right, it's pushing, it's this member is under tension, right? The member itself is under tension, it's being pulled, it's also pulling on B. If something's pushing on B, right, that's this member being in compression, right? You're compressing this member, the member wants to push back on that point. So we basically go through and we solve the conditions of equilibrium at each pin, right? And you wind up getting a set of equations, and you basically just walk through it. You solve the forces here, you transmit them through the member, you know the forces, you know some of these forces, you solve them at each joint, and we're going to do an example. So you just go from joint to joint and solve the system of forces. There are some special loading conditions that we have. Some of this is in your textbook is sort of a special section. So I'm not going to really test you on this, but you should be aware of this. So for example, this setup here, you've got dB and EC, right? There's forces along each of these. You can basically draw a force parallelogram. All this is saying is if you have intersection of um, straight line members, right? The forces are acting sort of equal and opposite directions along those straight lines, and that they're equal, right? So FAC has to equal FAE, and FAB has to equal FAD. Forces in opposite members are equal when a load is aligned with a third member. So here's an example of BD, right? This pin joint here has some forces acting along. Now notice these are both in line with each other. There's an external force P applied collinearly with C. So you know that this member AC is acting to oppose this force P. However, in this scenario here, this picture B, let me see, is that the next bullet? No. This position, or this load now, this member AC has no load on it, right? So this is now a zero load case. So there's no load on this member AC. And then finally, you can have a situation like this at the bottom, right here, where the force members, if they're connected and aligned, right, you have forces acting from one member to the other. However, if they're just if they're not aligned, right, like this, and there's no other members, you have two force members. This is the key. Two force members connected at a joint. There's zero force here unless they are aligned with each other. And you try to recognize these situations. For example, this is a truss analysis. And all they've done is they've highlighted in green the zero force members. So you can see here, right, you've got two members aligned here. This is a zero force member. You've got, in this case, you've got two members aligned again, two members aligned over here. This is also a zero force member. And then this is also a zero force member because the force is being transmitted directly through HJJL. All right, space trusses. I'm just going to go through this again for an FYI. 6 members, 4 joints, right? This is just the simplest space truss. So when you see things in 3D, like, Epcot Center or, some structure down there, it's made up of these, these tetrahedrons, which is just called a space truss, right? Because it's 3 dimensions in space. Let's see. These are the equations for equilibrium. Yeah, you can basically do the same thing with a 3-dimensional truss that you do with a 2-dimensional truss, except in this case, right, the points are going to each have forces acting in, any of the 3 dimensions. So it's not just a 2D analysis.